In this video, we're going to cover section 1.13, the pre-equilibrium approximation. So like the steady state approximation, the pre-equilibrium approximation is also used in the evaluation of reaction mechanisms. This approximation is used when equilibrium among a subset of species is established before product formation occurs. So let's consider the following reaction, where we have two reactants in equilibrium with an intermediate, and this intermediate will eventually decay to product. Now, if the forward and back reactions involving the reactants and intermediate are more rapid than the decay of the intermediate to form products, then the reaction can be viewed as occurring in two distinct steps. So long as, one, the equilibrium between the reactants and the intermediate is maintained during the course of the reaction, and two, the intermediate undergoes decay to form product. This description of events is referred to as the pre-equilibrium approximation. And this approximation is appropriate when the rate of the backward reaction of the intermediate to form reactants is much greater than the rate of product formation, a condition that occurs when the magnitude of the rate constant k minus 1 is much greater than the magnitude of the rate constant k2. The application of the pre-equilibrium approximation in evaluating reaction mechanisms containing equilibrium steps is performed in the following way. We first start off in a very typical manner where we describe a differential rate expression for the product formation. And for this particular mechanism, we see that product is being formed from the intermediate with the rate constant K2. So that will be the term that will describe the rate of product formation. Now, the concentration of the intermediate, this can be rewritten by recognizing that this species is in equilibrium with the reactants. Thus, we can use the equilibrium constant, which we know is a ratio of those two rate constants, the forward and the backward rate constants. We can equate that to the ratio of the concentration of the intermediate to that of the concentration of each of the two reactants. In doing so, we can solve for the concentration of the intermediate as a product of the equilibrium constant and the concentrations of the reactants A and B. Now that we have a solution for the concentration of the intermediate, we can simply substitute that into our rate expression for product formation. And in doing so, we're left with the following rate expression that describes the rate of product formation, which is dependent upon the rate constant K2, the equilibrium constant, and of course the concentrations of A and B. We can describe this as K effective, and K effective in essence is K2 multiplied by K1, all divided by K minus 1. So this expression shows that with the pre-equilibrium approximation, the predicted rate law is second order overall and first order with respect to both reactants A and B. Also, the rate constant for product formation is not simply K2, but is the product of this rate constant with the equilibrium constant, which in turn is equal to the ratio of the forward and back rate constants. So now what I'd like to do is to analyze the pre-equilibrium approximation. And we'll do that by taking the same reaction mechanism that we just discussed, but applying the steady state approximation, and look at the result of the steady state approximation and compare that to the result that we get when applying a different approximation, that is the pre-equilibrium approximation. So this is the mechanism that we just discussed. And so let's apply the steady state approximation to this mechanism. So if we solve for the rate of product formation, it's going to be equal to K2 times the intermediate concentration. And because I is an intermediate, we must solve for its concentration and substitute that term into this expression. So we must solve for the rate of the intermediate concentration with time as well. This species is involved in all three steps. It's involved in the forward reaction, it's involved in the reverse reaction, and the decay to product. So we have three terms associated with the change in concentration of the intermediate with time. So those three terms are as follows. We have a K1 times the concentration of A and B, minus a K minus 1 times the concentration of the intermediate, and minus K2 times the concentration of the intermediate. Now, if we apply the steady state approximation, we can set the net rate of change of the intermediate concentration to 0. In doing so, we can equate equation 2 to 0, and we can rearrange or solve for the concentration of the intermediate. And that's shown here. So now we can substitute expression 3, our solution for the intermediate concentration, into our original expression 1, and we end up with the following. We can collect the rate constants and place them in brackets out front, and we can equate this entire bracketed quotient as the effective rate constant for this reaction mechanism. As we saw when we used the pre-equilibrium approximation, we still have a second order rate law, first order with respect to A and first order with respect to B. What we also observe is that the effective rate constant is slightly different than what we obtained from the pre-equilibrium approximation. But recall that the pre-equilibrium approximation, what must hold true is that the rate constant for the reverse reaction, that is, for the intermediate back to reactants, that the magnitude of this rate constant be much greater than the magnitude of the rate constant for the intermediate decaying to product. So under this particular condition, we see a reduction in K effective in the following way. So when we state that K minus 1 is much greater than K2, what we're saying is that in the denominator, this term is much smaller than the K minus 1 term. As a result, we can make the approximation or the assumption that this is going to be our effective rate constant under those conditions. Now note that I canceled off K2 relative to K minus 1, but that doesn't delete K2 from the numerator. What we're doing is we're comparing the magnitude of two rate constants and saying, because the size of K minus 1 is much larger than K2, that in effect, although K2 still exists, it's going to be quite a small number relative to the magnitude of K minus 1. So we can treat that as now being our effective rate constant. And this is the same effective rate constant that we obtained when applying the pre-equilibrium approximation. So you can use the pre-equilibrium approximation if you have some insight that there is an equilibrium established between reactants and some intermediate. If you don't have that information, you can simply apply the steady state approximation. Yes, you'll end up with a different effective rate constant, but then if you wish to apply the pre-equilibrium condition at this stage, you're going to end up with the same result as we obtained from the pre-equilibrium approximation. So the pre-equilibrium approximation can save you a little bit of time in developing a rate law expression for a reaction mechanism if you have some insight that there is an equilibrium at some point within that reaction mechanism. Otherwise, you still have the steady state approximation that you can use to devise and develop a rate law expression for a complex reaction mechanism. So if you have any questions about the pre-equilibrium approximation, by all means, send me an email. Thank you.